When we talk about the future of technology, two terms come up all the time: classical computers and quantum computers. We use classical computers every single day, but quantum computers are hailed as the next giant leap. So what's the real difference between them, and why is quantum computing such a game changer? Let's break it down in a way that makes sense, without needing a PhD in physics. Every device you use, your phone, your laptop, even your smart TV, is a classical computer. At their core, they all work with bits. Think of a bit like a light switch. It can either be off, which we call a 0, or on, which we call a 1. Every photo you take, every video you watch, every app you open, is just a massive collection of these tiny switches flipping on and off at incredible speeds. For decades, we've gotten really good at making these switches smaller and faster. Modern processors have billions of these switches, called transistors, performing trillions of calculations every second. It's truly mind-boggling. But here's the key thing about classical computers: no matter how fast they are, they can only do one thing at a time. They follow a set of instructions step by step, evaluating each possibility one after another. Now, let's talk about quantum computers. These are a completely different beast. Instead of bits, they use something called qubits, or quantum bits. And qubits play by the wild rules of quantum mechanics. A qubit isn't stuck being just a 0 or a 1. Thanks to a wild concept called superposition, it can be both a 0 and a 1 at the same time. Imagine you're trying to solve a giant maze. A classical computer would be like a person who tries every single path, one by one, until they find the exit. They might be super fast, but they still have to check each dead end. A quantum computer, on the other hand, is like someone who can explore all the paths at once. This ability to exist in multiple states and explore many possibilities simultaneously is where quantum computers get their incredible power. But that's not all. There's another quantum trick called entanglement. When two qubits become entangled, they're linked in a mysterious way. The state of one qubit instantly affects the other, no matter how far apart they are. Einstein famously called this spooky action at a distance. This connection allows quantum computers to perform complex, coordinated calculations that are simply impossible for classical computers. So what does this actually mean in the real world? Let's imagine trying to crack a super secure password with a billion possible combinations. A classical computer, even a supercomputer, would have to try each combination one by one. It could take years, centuries, or even longer. A quantum computer, using superposition and entanglement, could theoretically check many of these combinations at the same time, cracking that password in a fraction of the time. But hold on, this doesn't mean your gaming PC is about to be replaced by a quantum computer. It is crucial to understand that quantum computers aren't just faster versions of what we have now. They're specialized tools for specific kinds of problems. For your daily tasks, browsing the web, sending emails, editing videos, playing games, classical computers are, and will remain, the best tool for the job. They're stable, reliable, and incredibly efficient at what they do. Quantum computers shine when things get overwhelmingly complex. They are designed to tackle problems with a massive number of variables and possibilities. For example, they can simulate how molecules interact. This could revolutionize medicine by helping us design new drugs and treatments with incredible speed and accuracy. They can also solve huge optimization problems, like finding the most efficient routes for global shipping networks, managing financial risk on a massive scale, or designing new materials for better batteries and clean energy sources. And yes, there's the big one: security. The same power that lets a quantum computer solve a maze quickly also lets it break many of the encryption methods we use today to protect our data online. This is because modern encryption often relies on the fact that it's incredibly difficult for classical computers to factor very large numbers. For a quantum computer, that's a much easier task. This has kicked off a global race to develop quantum-safe encryption to protect our digital world before large-scale quantum computers become a reality. There's another huge difference we need to talk about: stability. Your laptop works pretty much anywhere. It's a robust and reliable machine. Quantum computers, however, are incredibly delicate. Their qubits are super sensitive to their environment. The slightest change in temperature, a tiny vibration, or even a stray magnetic field can cause the qubits to lose their quantum state and introduce errors. This is called decoherence. To prevent this, most quantum computers have to be kept in extremely controlled, isolated environments. We're talking about massive, refrigerator-like structures that cool the quantum chip down to temperatures colder than deep space, just a fraction of a degree above absolute zero. This fragility is one of the biggest engineering hurdles scientists are working to overcome right now. But despite these challenges, the progress is astounding. It took classical computers decades to go from room-sized machines to the sleek devices in our pockets. Quantum computing is still in its infancy, but giants like Google, IBM, Microsoft, and Amazon, along with countless startups and research labs, are making breakthroughs every year. So, think of it this way: classical computers and quantum computers aren't competitors. They're partners. In the future, we'll likely see a hybrid approach. Your classical computer will handle all the everyday stuff, but when it hits a problem that's too complex, it might send that problem to a quantum processor for a solution, much like how a main processor in your computer sends graphics tasks to a dedicated GPU today. In summary, the difference between classical and quantum computing is fundamental. It's like comparing a bicycle to an airplane. A bicycle is great for getting around town, and it follows a clear, linear path. An airplane operates in a completely different dimension, the sky, and can travel in ways a bike simply can't. Classical computers process information one step at a time. Quantum computers harness the bizarre physics of the very small to explore a vast landscape of possibilities all at once. Classical computers built the world we live in today. Quantum computers are being built to solve the challenges of tomorrow. Thanks for watching. If you found this explanation helpful, don't forget to like this video and subscribe for more deep dives into the future of technology. See you next time.